it's going to work. Okay, so today we're going to actually talk more about that thing that blew your mind a while ago about local bond theory versus MO theory, and this idea of hybrid orbitals like sp hybrids and sp3 hybrids and so on, not really being supported by experiment. Okay, so I want to go through the experimental evidence that kind of talks about our bonding theories as opposed to our structural theories, and so on. So local bond theory or valence bond theory, I've heard it called both. I mean, do y'all recall discussing this? What has it been called in your educational?
Valence bond theory.
Valence bond is what you've heard most often? Okay. Yeah, so this is the bonding theory you grew up with, right? This is the thing that you use the Lewis dot structure to produce, or you use to produce the Lewis dot structure. So there's 2 electrons between every pair of atoms, and that makes a covalent bond. You know, if an electron is stolen or completely transferred, that's an ionic bond. If the electrons are completely delocalized, that's metallic bonding. So in our freshman chemistry, we really talk about those main 3 types of bondings: ionic, which really isn't a directional bond at all. It's just Coulombic charge holding things together. Salt crystals, sodium chloride. Metallic systems, there's really no covalent bonds there. There's just, again, a sea of electrons holding the nuclei together. That's why they conduct electricity. But then we get to the nonmetals, and we have covalent bonds. And this is the model for those, for HCl. It's not completely ionic. It's not pulling the electron off the hydrogen. It's sharing those 2 electrons. So hydrogen's happy. It has a 1s2 configuration. It's got its 2 electrons. And chlorine's happy. It gets to count those other 2, that extra electron, and it has a 2p6 or 3p6, depending on the row. So 3p6. Everybody has their filled subshells. And because they're sharing the electron, that's covalent. That's what that word means. It's in both valences at once. And these 2 bonds are what make these 2 electrons are what make a bond in the local bond theory. These noble gas configuration, where we have that full shell in the P shell, that's unusually stable. We see that from the first ionization energy data. So for atoms, we can look at the ionization energy of atoms, and the noble gases have the highest ionization energies. It's harder to pull those electrons off. You see how unequal shielding or incomplete shielding as you add protons to a nucleus and you add electrons, all of the electrons get pulled closer to that nucleus, because think about it. If I have an electron in the px and an electron in the py, and I put an electron in the pz, that pz, it has an independent view of the nucleus. And so the px and py don't really shield the extra proton I added when I move to the right in the periodic table. So all of the electrons get closer to the nucleus. The radius of the atom shrinks as we go from left to right in the periodic table. And it's really hard to ionize those noble gases because they have that stable electron cloud. So this is all very well thought out in terms of trying to get an octet. So this is what we call that octet rule. We like to have molecules that have 8 electrons nearby, and it's strongly adhered to by carbon, nitrogen, oxygen, and fluorine. So most of our molecules that use carbon or nitrogen or oxygen and fluorine will form double bonds based upon the octet rule. Make sense? We just think of let's just think of like carbonic acid. So you see CO3, 2 minus. Okay, so we've got carbon. Let's count up all of the valence electrons that we have. So we have 4 valence electrons from carbon, plus 3 times 6 from the oxygen. Okay, plus 2 more from the negative charge. Okay, so it looks like 24. Okay, so let me scoot this carbon over. And we're just going to make single bonds first. Okay, so we've used up 6 electrons in making our single bonds. So minus 6 bonding electrons. That's the BEs, okay? So we have 18 non-bonded electrons that we can put on this molecule. And typically we want to put them on the atom that wants them the most. So between oxygen and carbon, which one is more electronegative? Yeah, so we're going to go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. Minus 18. We're out of electrons, and so we're done with the Lewis dot structure. However, carbon only has 6 electrons that it can claim. And so it's going to pull down. See, again, we've got bonds. Why make double bonds? It's because of this octet rule that we're making double bonds. So it's that octet rule that's driving our double bonding in this molecule. Okay, nothing to do with pi electrons, nothing to do with unused p orbitals. Let's not think about that right now. This is Lewis dot theory. This is just an octet rule thing. Okay, so don't let your mind wander into other stuff that you know. This is freshman chemistry. We don't know about p orbitals, right? We don't know about pi bonds. We know we can count to 8. We're very young. Okay. All right. So we're going to take 2 of these and share that with that hungry carbon, and we're going to make, and then you get to organic and you talk about resonance, and you're like, why'd you choose that one? Well, okay.
I was going to say.
Yeah, exactly. So this oxygen's up here, and then we have a carbon, and then we have an oxygen. And I always like this too, because if we look at formal charge, these 2 oxygens are -1, formal charge. Carbon brings 4 electrons to the party, and it can claim 4 if we divide them equally. They're covalent sharing. And this oxygen brings 6 to the party, and it can claim 6. And so these have 0 formal charge. So not only does this one satisfy the octet rule, it also has the smallest set of formal charges, and we're happy about that.
And it matches the negative charge that we have.
Yeah, and so it's all good. Now, sometimes it's really curious, carbon monoxide and others, where the formal charge would drive one structure, the octet rule would drive another structure, and so the formal charge complication with the octet rule can be difficult. It doesn't always work out cleanly. But in elements in periods greater than 2, so third row and above, like phosphorus, sulfur, bromine, xenon. I just picked a few that I know have some really crazy Lewis dot structures that have more than 8 electrons around the middle atom. And I've heard people call that expanded octets, which absolutely I hate. That is dumb. What is an expanded octet? I mean, if this is 8, is this an expanded octet? It's just a bigger 8. I don't understand. But phosphorus pentachloride. That phosphorus is sharing 5 electrons and has 5 single bonds. And they call it an expanded octet. There's nothing 8 about that at all. It just has access to the 3D orbitals is what the deal is. Yeah. Whereas the carbon doesn't, and nitrogen doesn't. Nitrogen's on the row 2, and it would have to use the 3D orbitals, which are out of reach for a moderate. I mean, you maybe could make it happen, but then that wouldn't be a stable molecule, and 2 of those things would fly off, and you'd get ammonia again. If you tried to make NH5 or NCl5. So that's a stupid term in my humble opinion. So then from the Lewis dot theory, we get to our LB theory, Lewis dot structures. This is essentially what I just did. Sum the valence electrons, create a single bond network. So I just wanted to review for you. This is the procedure for producing a Lewis dot structure. Place the non-bonded pairs on the most electronegative atoms first. Subtract these from the non-bonded electrons. If any electrons remain, stick them on the central atom. And then form double bonds to give an octet for carbon, nitrogen, oxygen, and fluorine. Or if you have other molecules, you might want to create double bonds to reduce formal charges. So like in sulfate, so SO4 2-. Okay, so we have 6 electrons for the sulfur, plus 4 times 6 for the oxygen, plus 2 for the negative charge. Okay, So that's 24, that's 30, 32. Okay, so then we have sulfur, oxygen, 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 oxygen. So 2, 4, 6, 8. We've used up 8. We have 24 left. Okay, and they go on the more electronegative atom, which would be oxygen. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24. So we're done. Okay, so there's sulfate, Lewis dot structure, freshman chemistry. We could put a bracket around this and call it a 2-, which is nice.
11 and 4-.
Yeah, and then this bottom part, the optional part, this is what I'm saying, create double bonds to reduce formal charges. So let's look at the formal charges. So oxygen comes in with 6 electrons, I'll say 6 VE, valence electrons, and it can claim, if we split this bond in half, it gets 1 from the bond that it's sharing, 1, 2, 3, 4, 5, 6, 7. So it's 7 electrons nearby, and we subtract that, so we have a -1. So that's the -1 formal charge on this oxygen, and it's on all of this type of oxygen. So if it's that same type of oxygen, you don't have to calculate it again. And then sulfur brings in 6 valence electrons, and it can only claim 4. So it has a +2 formal charge. And so you can think of formal charge as, again, it's formal, meaning formalism, okay, not how it's dressed with a tie and a jacket. Okay, so it's a formalism, and you look at separation of charges, you got a +2 in the middle, and you have these 4 -1s around it, and how can I reduce that set of charges? I can start to make double bonds. And so this will tell you where the double bonds go. They flow from the negative atoms to the positive atoms, again, because of the charge. And so we're going to make double bonds. And resonance structures would say that, you know, it doesn't matter which one you make, you can go from all of these resonance structures. And you can count up the resonance structures, and that gives you some idea of the stability of the structure and all kinds of things that you learn in organic. Okay. And so if we did make double bonds, let's just pick a couple here. So all this looks familiar, I hope. It's a graduate class, okay. And so the sulfur now has 6 nearby electrons that it can claim, and it came in with 6 valence electrons, so it's good. Can't do this with oxygen because oxygen's on row 2. And so if you could get oxygen to bond to 4 things, it wouldn't have those double bonds. You know, it would just share 4 electrons, and it has it doesn't have those d orbitals nearby like sulfur does in row 3. Okay, so that's a little bit about the formal charge and the Lewis dot structures. Totally familiar with you, yes? And then we treat each one of these things here, like this double bond area is an electron domain. And so that has 4 electron domains. And that equals a tetrahedral electronic structure. So then that tells you the 109.5 angles and so on. So all of this is familiar. In fact, I know you have to know this because you did all the symmetry, and you can't do the point group without knowing this. But I'm just reviewing this just to make sure you use those Vesper shapes then to generate the 3D molecular structures. So let's look at an example. I can do water Lewis dot structure practice. We've already practiced a lot, so I'm just going to show these on here. Because of those lone pairs on the oxygen, we have 4 electron domains. And so that means that oxygen is tetrahedral electronic structure. I'm going to underline electronic because this is not a tetrahedral molecule, okay? That is a bent molecular structure. And I'm going to highlight that molecular, okay? So there's two types of structures. There's the electron cloud structure, and then there's the molecular structure, where the atoms are located and what shape that is. You cannot call water tetrahedral. It only has 3 atoms. There's no way you could put 4 things around a center point with 3 atoms, okay? So when I just want to cry, that's where my hair went. People looking at water and put tetrahedral down as the point group, okay? It's gone, you know, because again, it can't be a tetrahedral point group. But the electrons around there, according to local bond theory only, the electron cloud around water is tetrahedral. Again, local bond theory. CO2, we form this, you know, basic structure first, and then carbon doesn't have an octet, and so we have to make double bonds, and so we end up with this structure here. And this is a linear, both electronic and molecular structure. 3 atoms in both molecules, one's linear, one's bent, according to Lewis dot structure. Okay, let's go to the spectrum. So here's our spectrum. This infrared spectrum is giving us rotational information, and rotational information will tell us something about the structure of the molecules. And water and CO2 are both in the atmosphere, so we just need a single beam spectrum and just look at infrared light coming off of a hot object, and we'll see absorptions related to things in the atmosphere. We'll see CO2 absorptions and water absorptions. And these are the water absorptions, and these are the CO2 absorptions. And if we zoom in, we see this structure here. If you take my undergrad class, you'll see that this is a P branch and an R branch that are related to the rotational structure of that molecule. And I'll sign in later. And this is a P, Q, and R branch over here in the bending mode of CO2. And these are the signals that you get from a linear molecule or a symmetric molecule, but for CO2 it's a linear structure, and so these are the signals we're getting to show that that is a linear structure. So hey, local bond theory and Lewis dot structure is telling us that we got the right structure for CO2 and water. That's craziness. We don't really see clear P and R branches, question mark, right? It's ugly. This is beautiful. Okay. All right. And so this asymmetric nonlinear rotational structure, since it's so crazy, we know water cannot be linear. And so the local bond theory with the non-bonded electrons and the Vesper shape, and it's tilted our water molecule, we're good. We know it has to be a bent structure for water and a linear structure for CO2. So the infrared spectrum confirms that local bond theory is giving us a good structure, bent versus linear. And it's useful for other molecules too that are more complicated, but this is just a real simple example in the infrared. So local bond theory is supported by rotational and vibrational spectroscopic data. But what if we send X-rays at these molecules? Okay, where we actually pull the electrons out of the molecule to see how much energy they have inside the molecule. So this is X-ray and UV photoelectron spectroscopy. So this is a way, if you think about the molecular orbital diagram, you have all of those energy levels with electrons in them. And if we hit those electrons with enough energy to pull them off of the molecule, it takes some energy. Let me just draw the energy level diagram. So this is let's just use our quantum numbers. N equals 1, N equals 2, etc. N equals 3. And they get closer and closer and closer together until there's an ionization limit. And so let's call this atom, and up here is atom plus. Okay? And so we'll call that spot right there atom plus. That's the energy of atom plus. So if we could just get that electron barely off of the atom with no excess energy, we would have separated it, but it wouldn't have any kinetic energy and wouldn't really be easily detected. But if we hit it with a photon like this, like an X-ray photon here, this piece right here is the binding energy. And this right here turns into kinetic energy. Of the photoelectron. So we've pulled this electron, it was sitting in this orbital here. It has come out of that atom, and now it has this chunk right here of kinetic energy. Now this is the length of the X-ray arrow. And so what if I had an electron here in this orbital?
You have higher kinetic energy.
Yeah, so the arrow is the same length. So I'll do my best to draw the arrow of the same length. Okay? So that's about right. So that's my X-ray photon. And look how much more kinetic energy that electron has. So if I could shine X-ray light at this sample, electrons are just flowing out of this sample. And then I need to filter them by their kinetic energy. And if I filter them by their kinetic energy, I know how deep they were in the molecular orbital or atomic orbital diagram. Okay? So I'm getting the bonding or the energy of those electrons if they're around an atom or if they're in a molecule. It's a way to probe the energy levels in that molecule by looking at the kinetic energy. Now, just for fun, how do we filter kinetic energy? Well, just think about a highway, and you've got a big turn, and you've got a Ryder truck and a Porsche. Okay. No, that's mass spectrometry. Never mind. We've got yeah, that's mass spectrometry. The Ryder truck and the Porsche. No, we've got now the ability to change the bank and the turn, and we've got cars going at different speeds. And so if we make the turn too sharp, the fast cars will fly off the turn, and the slower cars will be able to make the turn. Okay, and so we could change that, but we're dealing with charged particles, and so we just put a positive charge here and a negative charge there, and we can filter those electrons by their kinetic energy because they all have the same charge. And so we just run a variable voltage here, and we plot the spectrum of what we get. And that variable voltage is filtering the kinetic energy, and we can do the math and convert that to binding energy right here. We can figure out how strong that electron was bound to that molecule. So if we put water here in the middle, and we hit it with X-rays or UV rays, UV will work for the bonding electrons. This is, if local bond theory were true, how many types of electrons do we have in this particular picture of water? The OH bonded electrons and the non-bonded electrons. So we have the lone pair electrons and the OH bonding electrons, and so we should see two peaks. If local bond theory is true, we should see two peaks. Does everybody agree with that? Yeah. Okay. And so let's take a Kahoot. Let's break it up. Okay. It's going to make me log in just a second. Okay. Three 373-177. That's your game pin. Is that every? Let's see, 1, 2, 3, 4, 5, 6, 7, 8, 9. Is it having trouble? Yeah. Can you tell what's wrong, Rachel?
It's the internet. It just won't.
Okay.
It's like Sam, it won't authenticate.
Oh, that's too bad. All right. 373-177. We're not close enough to Halloween. Sometimes they put pumpkins in here for the 2 O's. That's right, the whole month, exactly.
They're already putting Christmas stuff on.
Yeah.
They got rid of all the Halloween decorations.
Okay. Do we have anybody that's not planned? Is that okay? Okay.
There's a lot of this.
Yeah, okay. Let's go. Okay, so this is just testing you. How many UVPS peaks do we get from this structure? So how many different types of electrons are there? Pretty good. Yes, so this would be an electron from the CH bonds, and all those CH bonds are identical. There's no reason why there would be any difference, so that would be one peak. Carbon-carbon sigma bond, another peak, and then the pi bond, another peak. So different types of electrons is what we're looking for. All right. Pretty much walked you through this one. That takes a while to understand what I'm saying here. Okay, very good. Very good. Okay. How many valence band UVPS, UV photoelectron spectroscopy peaks would be for CO2? I actually been taking this today. I screwed this one up, so pay attention.
You should never change your answer, man.
Y'all probably did exactly what I did. Yeah, a lot of people put 2 because I didn't see the lone pairs. Yeah, and so so sigmas, pi's, and lone pairs, 3 peaks. Okay. Okay, I think this is getting close to fourth of that 5. So, water. If oxygen is sp3, so we haven't talked about sp2 and 3 today, but that goes back to Vesper theory. You should be familiar with it. So we try to remember what we mean by sp3 and what it says about those lone pairs. Okay, very good. So if we try to force, and this drives me crazy that somebody actually did the math, to force Gaussian to use local bond theory, okay, and how it populates its orbitals. And I just want to strangle the person that did that. But Gaussian actually predicts water to be sp2. Yeah, sp2. So if water were sp2, maybe, what would that do to those lone pairs? So so think about an sp2 water. Think about what structure would give sp2. Now that would change the HOH bond angle to like 120, right? maybe slightly less because, again, sp2 is trigonal planar electronic structure. So, but yet we've got all these lone pairs. So try to get your mind around what an sp2 would give you. There's only 4 options. So. All right, good. I talked the whole time. Yeah, so sp2 would be an sp hybrid with 2 electrons in it, and the unused pz orbital would have 2 electrons in it.
Yeah, I got it.
Yeah. Yeah. Okay, so let's see. So you're familiar now with what XPS would give with these different kinds of, if it was local bond theory, right?
Well played.
And the goal today is, yeah, excellent. Okay, congratulations, good job, all that business. Okay, let me go back and turn the display capture off, go back to PowerPoint. Okay, so here we are, XP, but we know that MO theory is very different. Look at the molecular orbitals, and you tell me whether you see any sp hybrids. It's not sp2, it's not sp3. There's no hybridization in molecular orbital theory. This is the atomic orbitals in their symmetry-adapted linear combinations and using symmetry because that's what waves would do in terms of interacting with each other. They would interact with symmetry, right, as they're governing equations on how they would interact. And we end up with these molecular orbitals in the middle. There are no sp hybrids in that middle molecular orbitals, or even on the oxygens or the hydrogens. Okay.
You create all the shapes from galaxies.
Yes.
How'd you get it to do those?
I can teach y'all how to do that. Yeah, I will do that. Okay, so if we hit this molecule with X-rays, what will we see? Look at the energy levels, right? And so if we go in, we see this spectrum. And we go a little, like with X-rays, we get some signals from oxygen, just the 1s electrons from oxygen as well. And so they have labeled them in this paper as the 1s binding energy oxygen electrons were 1A1. So they labeled them with the Millikan symmetry notation in that paper. And then this was the second A1, this was the third A1. There was a B2 and a B1. And so the spectrum matches MO theory. And there was a little different order than what we saw in Gaussian, but that's still the same labeling. So that's amazing. In fact, just to show you, here's the actual paper. Okay. And so this is what the spectrum looks like. The oxygen 1s is at a higher binding energy than what we see here. It's off scale, I guess I would say. And so that's the first A1 orbital here. And then we have the second A1 and the third A1. So the A1s, their labeling scheme, like I said, there's really no convention for how we label molecular orbitals. And so they were just labeling them with their Millikan symmetry. But as far as the numbers they put in front, they just labeled them in order of symmetry. And then from lowest to highest, the first A1 was 1A1, then 2A1, then 3A1, and so on.
What's the intensity tolerance?
Yeah, so think about the intensity. That's a good question. You can think about intensity as probability, okay? But probability of what? And you can see with that 2A1, it's kind of smeared out. But with the 1B1, it's really sharp and strong. But it does kind of look like the areas under these curves are similar, okay? And so... this, I'm hand waving. I don't know exactly the perfect answer, but when I look at that, I think, okay, it does look like the area under the curve is somewhat related to the number of electrons that you have, but it's also related to the cross section of that orbital. Meaning, I've got an orbital with an electron in it, and I'm trying to hit that orbital with an X-ray. Okay, and if that orbital is spread across a whole huge molecule, I might get a smaller signal than if that orbital is located on, say, an oxygen atom, the 1s orbital. So the 1s orbitals have really high intensity peaks because they have a huge cross section. The electron's located in a very small space and it's easy to hit. Whereas the broader peaks, as they're spread out, get them more difficult to hit. but also you see there's the spread as well is related to the sort of the uncertainty of that energy level in that substance. So if half the molecules have an orbital here and the other half have there, but in a different kind of molecular orbital, all of those orbitals are really close and the same energy, this gives you some sort of idea of where that orbital is smeared by the environment of that molecule. There's a lot that goes on into these intensities. I know it's cross-section. I know it's number of electrons. I know it's the environment of that molecule that might smear the energy of that orbital up or down based upon hydrogen bonding or bonding influences on that orbital. So those are the things that go into those intensities. Okay, but it does look interesting how this sort of inverse, pattern here from strong, they kind of gradually get weaker and more spread out. But what's interesting is look how it matches all four of these. So this one is the highest occupied molecular orbital. That one down here is in order. Now these two are switched, okay? And it's just because Gaussian, I used a pretty low level of theory in creating these molecular orbital energies. Okay. I think I used like just Hartree-Fock 6-31G, I mean really low, or maybe even 321G. Just wanted to get the pictures. So we could go in and really crank up the level of theory on water and maybe get a more accurate ordering of those energies. But the other interesting thing, though, is that this XPS spectrum really does match molecular orbital theory. It doesn't match local bond theory at all. So what do? We have two theories. Do we throw local bond theory out now because XPS shows that it's a fiction in terms of its understanding the electrons? I mean, that's what it's using to come up with the structures, is the electronic structure, and we just showed the electronic structure that it's using is wrong. It's totally a miracle to me that it works, because the thing it uses to come up with those structures, where the electrons are, is fiction. And yet it gets the structures right. That blows my mind. It totally blows my mind. And so how do we evaluate theories? I don't want to throw that theory out. It's useful. I can do it with a pencil and paper. I don't need a computer. I don't need Gaussian. I can do water and CO2 and even up to DNA, with Lewis dot structures and Vesper theory. So we evaluate theories. This is something you will probably not get in any chemistry course, because we just tell you the theories. We don't tell you how to evaluate them. And so these are three criteria that you use to evaluate theories. This doesn't have to be scientific theories. This could be a historical theory. Did Shakespeare write all of his plays, right? You could have theories related to anything. And these are the criteria on how you evaluate theories. One is called explanatory power. How well does the theory match the data? And these are the things that pchemists love. R-squared values, RMS values, maximum deviations, and so on. So if we have low RMS values, good R-squareds, when we plot theory versus experiment and we get a line that goes through those and we say, well, we've got a really clean R-squared value. Or when we have things that aren't really easy to do in regression analysis, we might get a root mean squared deviation value or mean absolute deviations where you take the sign into account. Then, we can evaluate quantitatively how good the match is. That's what this is, explanatory power. There's also explanatory scope. So how large is the data set and how diverse is the data set? Is it just for carbon atoms, or is it carbon and oxygen, or do we get into the third row, or do we go to the whole periodic table? How diverse is the data set? Are we looking at different kinds of data, rotational spectra, vibrational spectra, visible, UV, X-ray? So if the data set's diverse and large and we match it all really well, we have a great theory. If it doesn't match that well, we have a less than great theory. And then this other thing, exceptions, right? Every theory you say, oh, there's an exception here, an exception there. Phosphorus, it has an expanded octet, Yeah. So ad hoc-ness, that's Latin for this, okay, for this. and big is bad. So these number of exceptions that you have, they harm your theory, So that's these are the special cases, and you can use these kinds of terms to think about different kinds of theories. You say, well, that theory has a lot of exceptions. I mean, that's why we complain about English language, right? It has so many exceptions, right? It's just that makes it difficult to learn, you know. And so you know what an exception is. You have a rule, I before E except after C, or in words that rhyme with neighbor and way, and all of these things. Those are ad hoc things that we've added in. You know. Okay, so let's evaluate local bond theory based upon this idea of things. So its explanatory power is big. You know, it with the Vesper shapes, they accurately model molecular structures. And there's a lot of molecular structures that it works on. In fact, it's good enough to give us all of those initial guesses for Gaussian. So we use Vesper theory, local bond theory, to give us our initial structures in Gaussian, and then Gaussian cleans them up. Okay. Its explanatory scope has a big hole in it. It matches rotation and vibration, but it does not match electronic spectroscopy, which is a mystery to me because it supposedly uses an incorrect theory on electronic structure to come up with accurate shapes. That's so weird. Yeah. And I guess, what is the valence shell electron pair repulsion theory doing? It's saying these electron pairs are repelling each other. If we would just take the word pair out of there, I think that's key to how it works. Where are the electrons going to be but where the atoms are? So if I have an oxygen here and I have two hydrogens, some electrons are going to be associated with those hydrogens, and those electrons repel the other electrons. And so they get the hydrogens far away from each other. But there are electrons on those oxygen atoms in the other p orbitals, and those repel the electrons in the hydrogen bond, the OH bonds. And so we still have, it's not electron pairs, and they're not associated with each bond exclusively, and not really in pairs of non-bonded electrons, but we do still have electron density that repels the other electron density. It's just not as easy as Vesper theory makes it out to be. And then ad hoc-ness, oh yeah, it's got the expanded octets and Octet Rule and all of that. So that's the ad hoc nature of local bond theory. So let's look at MO theory. You know, its explanatory power is big. Those MO theory accurately predicts the modeled molecular structures. We get really good structures out of Gaussian, and even, you know, if we were really, we can't do these by hand. I mean, I can't solve for the molecular structure of water by hand using molecular orbital theory. I can give you the shape of it. I can tell you what atomic orbitals are there, but can you tell me the bond length of your hydrogen peroxide? No way, right? Or even the angles, right? Vesper theory tells me the angles. That's pretty cool, but yeah, MO theory, no, I can't really do it by hand. But Gaussian, if I get the computational chemistry going, I can calculate those structures really well. The scope is great. It matches rotation and vibration and electronics. So it fills that hole that's left by local bond theory. And as far as I know, there are no ad hoc parts to it. It is missing the electron correlation. Those really aren't exceptions, though. We know what we're missing, and we're trying to fill in that hole. But we're not saying for this type of molecule, we got to do it this way, and for that type of molecule, we got to do it that way. It's just we treat all the molecules the same with a given model chemistry. So if we're using HF theory, we use that HF theory for hydrogen, for water, for CO2. We treat all the molecules the same. Okay. So how do we choose? Right? I mean, we have the easy theory. Y'all seen the easy button? Local bond theory is easy, and it can do molecular structure. So if you're just coming up with a structure, you need an initial guess for Gaussian, don't throw away local bond theory. Don't get rid of Vesper theory. Don't, forget about SP hybrids, because they tell you about 109.5 degree angles and 120 degree angles, and all of that stuff is still good for molecular structures as an initial guess or a rough guess. They will also help with the rotational and vibrational structure. You can get a close view of the rotational constants and the reduced mass of a molecule rotating using Vesper shapes and so on in geometry. But if you want to do electronic spectra, you're going to need to use molecular orbital theory. And this is the controversial piece in organic chemistry, if you really want to understand bonding and mechanisms. Now, we do a lot of mechanisms using local bond theory and pushing electrons, you know, and a lot of times I think that works out just by coincidence. But you'll find things that can't be explained using local bond theory that you have to go to molecular orbital theory, like the Diels-Alder reaction and things like that, where you have this concerted interaction of molecular orbitals that can only be explained with molecular orbital theory, can't really be explained well with local bond theory. So how do we choose? Well, we choose the appropriate theory, and Gaussian does all of these with MO theory, and Gaussian's fairly easy, okay? So you use local bond theory to put input into Gaussian or software like it, and then you can calculate your structures, which give you your microwave and your infrared spectra, and then you can calculate your molecular orbitals, which give you your visible spectra, and it gives you the molecular orbitals so that you can understand things like nucleophilic attack and electrophilic attack, because you can map the electron density and the charge around the molecule, and you can say, here's a positive region, here's a negative region. All of that's based on MO theory. Okay. Now, what are your reactions? Because y'all are also taking graduate organic. So I'd like to get your feedback here, questions or comments. Nothing.
And I had a question about the Gaussian mechanisms. So you can export them all at once, or do you have to do one by one?
I had to do them one by one, like that molecular orbital diagram.
Yeah.
Now, there is, for Gaussian, I'll tell you what to do, but then later on in a lecture, I'll show you, okay?
Yeah. No, I know how to do it.
Yeah, so you bring in the checkpoint file. So we've been dealing with the log file, which has the output. The checkpoint file has all of the wave functions for the molecule, which are the molecular orbitals. So you read in the checkpoint file, and there's a feature in Gauss View called the molecular orbital editor, MO editor. And you go to that, and then you can click on it and say, go ahead and create what they call cubes. What they mean is cubes of data, right? Okay, so they're creating a cube of data around the molecule, and then they're mapping a surface that captures, say, 95% of the electron in that orbital. So it's a 95% surface of that molecular orbital inside that cube of data. So they're saying all of the points that have a certain value, connect them. So you have this cube of data points with really small numbers out at the far edges of the cube, bigger numbers towards the center of the nuclei where there's a bigger chance of finding an electron. And so you're just trying to pick like a 0.05 or a 95% surface, and you're connecting all of those surfaces, and it's creating that molecular orbital, and then you can display it. And so that's what's being displayed. And then you can also say molecular orbital diagram, and it'll take all those energy levels and sort of create an MO-like diagram. If it's a diatomic, it'll have the degenerate energy levels and so on that you're familiar with. But if it's something like water, there aren't any degenerate energy levels, so it's just stacked up with their relative spacing, fairly accurately portrayed. And so that's a way to get that MO diagram for water and for any molecule, yeah. Now, the molecular orbitals are really confusing. You see some of the water ones, you know, we go up to these higher energy ones, like this guy up here. You know, that's a really crazy looking molecular orbital that comes out of Gaussian, but it's that PZ orbital on oxygen, you know, out of phase with those hydrogens. And so that's what's trying to be shown there. But Gaussian's letting those electrons have a little bit more freedom, and so they're expanding where they want to and not expanding where they don't want to. Okay, so that's it for today. And next time we'll do a review, and on Monday will be a test over point groups, character tables, reducible representations, and all of that stuff. So this middle section of the course, we'll wrap it up.